You wake up. It's still dark. The air is so cold that every breath you take feels like swallowing broken glass. Your skin is numb. Your fingers won't close properly. And the person next to you is shaking so hard you can feel it through the ground. You're somewhere in what is now England, roughly 900,000 years ago. The landscape around you looks like southern Scandinavia. Pine forests, frozen rivers, patches of snow that won't melt for months. And you don't have fire. You don't have the faintest idea what fire is. No human on this part of the planet does. No campfire, no torch, no warm glow to huddle around while you wait for morning. Just the cold, and you, and whatever you can figure out before it kills you. That's not a hypothetical, that's an archaeological fact. And the question of how anyone survived it has been bothering scientists for decades. Here's why this is such a strange problem. We have extremely solid evidence that ancient humans were living in freezing northern climates hundreds of thousands of years before we have any evidence that they could make or even reliably control fire. In 2011, archaeologists Will Robrooks at Leiden University and Paolo Villa at the University of Colorado published a landmark study in the Proceedings of the National Academy of Sciences. They reviewed the entire European archaeological record and reached a conclusion that made a lot of people uncomfortable. There is no robust evidence for habitual fire use in Europe before roughly 300,000 to 400,000 years ago. Not occasional use. Not maybe they had it, we just can't find it. No consistent, widespread, we know how to do this and we do it all the time evidence. But humans were already there, hundreds of thousands of years earlier, in the cold. Let that sit for a second because the math here is genuinely unsettling. In May 2013, a team led by Dr. Nick Ashton from the British Museum and Dr. Martin Bates from Trinity St. David's University in Wales discovered something on the beach at Happisburgh, a small village on the Norfolk coast in England. The tide had just gone out and exposed a layer of ancient sediment, and pressed into that sediment were footprints, human footprints. At least 5 individuals, adults and children, walking through an ancient river estuary. The team recorded them using 3D photogrammetry before the next tide washed them away forever. When they announced the findings in February 2014, the dates were staggering, between 850,000 and 950,000 years old, the oldest hominin footprints ever found outside Africa. And at that site, 900,000 years ago, with winters that would put modern Scandinavia to shame, there is zero evidence of fire. None. No charcoal, no ash, no burned bone, no hearth, nothing. Whoever left those footprints walked through a frozen world without any of the things we automatically associate with cold weather survival. No fire to warm them, no fire to cook their food, no fire to scare away predators, no fire to light the 16-hour winter nights. So how did they not die? That's the question. And the answer isn't one thing. It's a collection of solutions that, when you see them all together, tell a story about how strange and tough and resourceful our ancestors really were, long before they figured out the trick that would eventually change everything. Let's start inside the body, because that's where the first line of defense actually was. You know that feeling when you step outside on a freezing morning and your body immediately starts doing things you didn't ask it to? Your fingers go white. Your skin tightens. You start shivering before you've even decided you're cold. That's not random. That's ancient hardware running ancient software. And it was built for exactly this problem. When your core temperature starts dropping, your body does something called peripheral vasoconstriction. The blood vessels near your skin narrow, hard. Blood retreats from the surface and concentrates around your vital organs, your heart, your brain, your lungs. Your extremities go cold because your body has decided, without consulting you, that your fingers are less important than your liver. From a survival standpoint, that's the correct call. Frostbitten fingers can heal. A cold heart stops. But ancient humans living without fire needed more than just blood vessel tricks. They needed to generate heat from the inside, and this is where it gets interesting because your body has a way of doing that, and most people have never heard of it. Brown adipose tissue, BAT. Most people know about regular body fat, the white stuff that stores energy and insulates you and accumulates in places you'd rather it didn't. Brown fat is different. Brown fat doesn't store energy. It burns it. Specifically, it converts chemical energy directly into heat through a process called non-shivering thermogenesis. Your body can warm itself without moving a muscle, without shivering, without doing anything visible at all. It just generates heat internally, like a furnace you didn't know you had. And here's where this connects directly to the question of surviving winter without fire. In 2021, a research team led by Watanabe published a study in Scientific Reports examining ancient remains from Tierra del Fuego, the southern tip of South America. The Fuegians, the indigenous people of that region, had lived for thousands of years in freezing, stormy conditions with minimal clothing. Charles Darwin himself, sailing through on the Beagle in the 1830s, was stunned to find people nearly naked in conditions that had his fully clothed European crew miserable. What Watanabe's team found was a variant of the HOXC4 gene that promotes the development and activity of brown adipose tissue. These people weren't just tough. They were genetically equipped to generate internal heat at rates that would give a modern human in a parka a run for their money. Without fire, your body is the only furnace you've got. And evolution, given enough time and enough dead people, will build a better furnace. But body heat alone doesn't explain everything. Not even close. Because there's a limit to what biology can do against a winter night that drops below freezing and stays there for 14 hours. You need something between you and the air. Without fire, what was that something? Let's start with the obvious. Caves. If you've ever walked into a deep cave, you might have noticed that the temperature barely changes. A deep cave in a temperate region sits at roughly 10 to 13 degrees Celsius year-round, regardless of what's happening outside. In the middle of a glacial winter, when the air above ground might be 20 or 30 below zero, a cave at 10 degrees is not warm. Nobody's comfortable. But it is absolutely the difference between dying tonight and dying next week, which, when you don't have fire, is a meaningful improvement. Cave walls block wind, which in extreme cold is almost as dangerous as the temperature itself. Wind chill doesn't just make cold feel worse. It accelerates heat loss from exposed skin so fast that a survivable temperature becomes a lethal one in minutes. A cave eliminates that. It's not a heated room. It's a wind barrier with thermal mass, and for a species with no fire, it was the closest thing to a building they were going to get. But here's the problem with caves. They're not everywhere. They're not even in most places. And the animals you need to eat don't arrange themselves conveniently near cave entrances. So what did ancient humans do when there was no cave? This is where the great ape connection becomes important, and it's a detail most people miss entirely. Every great ape species on the planet, chimpanzees, bonobos, gorillas, orangutans, builds a sleeping nest. Every single night. They bend and weave branches into platforms, sometimes on the ground, sometimes in trees, and they sleep on them. This is considered a form of material culture, a behavior so consistent and so widespread among great apes that researchers believe it stretches back millions of years to a common ancestor that we share. Now think about what that means for the humans at Happisburgh 900,000 years ago. They didn't need to invent the concept of building something to sleep on. They inherited it. Their ancestors had been building sleeping platforms for millions of years before anyone walked north into a cold climate. The technology wasn't fire. The technology was arranging the stuff around you into something more comfortable and more protected than bare ground. And when the climate got colder, that same instinct, that same behavior would have driven them to build more substantial structures. Not mammoth bone houses, that comes much later, but windbreaks, branch shelters, anything that put a layer between your body and the moving air. Without fire, shelter isn't about warmth. It's about reducing how fast you lose the warmth you've already got. And that distinction matters more than it sounds like it should. Now, here's a pattern interrupt for you, because this is the part where most people make a critical assumption and get it wrong. The assumption is that ancient humans in cold climates were alone. A person, or maybe a small family, huddling in a cave trying not to freeze. The lone survivor. The individual against the elements. That is almost certainly not how it worked. And the reason it didn't work that way is physics. A single human body generates roughly 80 to 100 watts of heat at rest. That's about the same as a dim light bulb. In a freezing environment without fire, one body can't keep itself warm. The heat radiates off the skin faster than the metabolism can replace it, and hypothermia sets in. But put 5 bodies together, or 10, or 15, and something changes. The total heat output increases, while the exposed surface area decreases. Bodies pressed against each other create a microclimate, a pocket of warmer air that none of them could maintain alone. This is called social thermoregulation, and it's not unique to humans. Emperor penguins do it. They rotate in massive huddles during Antarctic winters, cycling individuals from the exposed outer ring to the warm center and back again. Rodents do it. Bats do it. Any social species in a cold environment eventually figures out that being close to other warm bodies is the cheapest heating system available. For ancient humans without fire, communal sleeping wasn't a social nicety. It was survival infrastructure. The group was the furnace. And this has a profound implication that connects directly to the question of why these people survived at all. A solitary human in an ice age winter without fire is dead. A group of 15 humans in a sheltered space, bodies pressed together, conserving heat collectively, sharing the biological output of 15 metabolisms instead of one, that group has a chance. Which means the social bond, the decision to stay together, to tolerate each other, to organize sleeping arrangements and coordinate movement, that bond was not a luxury. It was a thermal necessity. You didn't huddle with people because you liked them. You huddled with them because the alternative was freezing to death in the dark. Community wasn't optional. Community was heat. Now, even if you've got the right body, the right shelter, and enough people to sleep against, you still need to eat. And what you eat matters enormously when fire isn't available to cook it. Here's something most people don't think about. Digesting food generates heat. It's called the thermic effect of food, or specific dynamic action, and it varies depending on what you eat. Protein has the highest thermic effect, at 20 to 30% of the energy content. That means if you eat 100 calories of raw meat, your body burns 20 to 30 of those calories just processing it, and that processing generates heat as a byproduct. Fat generates 5 to 15%. Carbohydrates are lower. Now, raw meat has a higher thermic effect than cooked meat because it takes more digestive effort to break down. This is actually one of the arguments evolutionary biologist Richard Wrangham has made for why cooking was such a transformative technology. It made calories easier to extract. But flip that argument around and something interesting happens. Before fire, before cooking, the very difficulty of digesting raw food was generating extra body heat. Your digestive system was working harder, burning more energy, and throwing off more heat as a result. It wasn't efficient. But when you don't have fire, your gut becomes a secondary furnace. And the harder it works, the warmer you get. And what were they eating? The answer, overwhelmingly, was fat. Bone marrow specifically. The inside of a large animal's long bones contains marrow that is extraordinarily calorie-dense, more than double the calories per gram of protein or carbohydrates, and it's almost pure fat. Before early hominins were proficient hunters, many of them were scavengers, arriving at carcasses after the predators had taken what they wanted. The lions ate the muscle. The hyenas cracked some bones. But a hominin with a stone tool could break open bones that no other scavenger could access and extract marrow that nobody else could reach. This is a genuinely underappreciated survival strategy. You don't need to be the strongest predator on the savannah. You don't even need to be a predator at all. You just need a rock and the knowledge that the inside of that femur is keeping you alive. At Kesem Cave in Israel, dating to roughly 400,000 years ago, researchers found evidence that early humans were practicing what amounts to delayed consumption, storing bones and extracting marrow weeks after the kill. They were treating bone marrow like canned food. That's not instinct. That's planning. That's someone looking at a pile of bones and thinking, I'm going to need these when it gets cold. Without fire, every calorie matters more. You can't cook food to make it more digestible. You can't smoke meat to preserve it. You can't render fat over a flame. Everything you eat is raw, and everything you eat costs more energy to process, which means the margin for error is thinner than paper. And the people who survived were the ones who found the richest possible food sources and extracted every last calorie from them. Here's another thing that most people get wrong about this question, and it's a big one. The assumption that ancient humans always stayed and fought the winter, that they planted themselves in a freezing landscape and gritted their teeth until spring. Some of them just left. Not migration in the way birds do it, not a single long flight to a warmer place, more like a gradual, multi-generational shift. When the climate got colder, some populations moved south. When it warmed up again, they expanded north. This wasn't a decision made at a meeting. It was a slow drift, measured in kilometers per generation, following the animals, following the plants, following the temperature gradient towards something that didn't kill you quite as fast. The evidence at Happisburgh itself suggests this. The human presence there 900,000 years ago may have been temporary. Ephemeral, the archaeologists call it. People passing through during slightly warmer seasons, not committing to year-round residence in a landscape that would be genuinely brutal in deep winter. The site at Pakefield, also in England, dating to about 700,000 years ago, appears to be from a warmer interglacial period, a window when the climate was almost Mediterranean. People weren't there because they could survive the cold. They were there because, for a few thousand years, it wasn't that cold. Without fire, the honest answer might be that many early humans survived winter by not being there for the worst of it. They tracked the seasons. They followed the warmth. They retreated when conditions became genuinely unsurvivable, and they returned when the world thawed out enough to try again. But not everyone left. And this is where the story gets genuinely strange, because some populations stayed in cold climates long enough for something remarkable to happen. Their bodies changed. Two biological rules describe this pattern, and they're both named after the scientists who first noticed them. Bergman's rule says that populations in colder climates tend to be larger and heavier because a bigger body has a smaller surface area to volume ratio, which means less heat loss per unit of mass. Allen's rule says that populations in cold climates tend to have shorter, more compact limbs because shorter extremities lose less heat. The Neanderthals are the textbook example. Broad trunks, short, thick limbs, high body mass, stocky, powerful, built like a wrestler who also happens to be a refrigerator. Every proportion of the Neanderthal body is optimized for heat conservation in a way that modern tropical humans are not. And that optimization didn't happen overnight. It happened over hundreds of thousands of years of living in cold European and Central Asian climates. Generation after generation, the individuals who retained heat slightly better surviving and reproducing at slightly higher rates than the ones who didn't. The caloric cost of that body was enormous. Stephen Churchill at Duke University estimated in 2006 that a male Neanderthal needed somewhere between 4,000 and 5,000 kilocalories per day. Sorensen and Leonard at Northwestern put the range at 3,000 to 5,500, depending on activity level and ambient temperature. That's 2 to 3 times what a modern sedentary human eats. Every single day, in an environment with no supermarkets, no agriculture, no food storage beyond whatever you could stash in the permafrost. Those bodies demanded enormous quantities of fuel just to keep running. Without fire, the energy equation becomes almost impossible. You can't cook food to extract more calories from it. You can't dry meat or render fat for storage. Every calorie you consume gives you less usable energy than it would if you could cook it first, which means you need to eat more, which means you need to hunt or scavenge more, which means you burn more calories moving. The numbers barely close, and for many individuals in many winters, they didn't close at all. And this brings us to what might be the most uncomfortable part of this entire story. The fire gap. Humans at Happisburgh, 900,000 years ago. No fire. Humans at Dmanisi in Georgia, 1.8 million years ago. One of the oldest sites of Homo outside Africa. Excavated by David Lord Kipanidze since 1991. Seasonal winters. No fire. 5 remarkably preserved skulls found there, including the famous Skull 5, discovered in 2005 and described in 2013, with a brain case of just 546 cubic centimeters, barely a third of a modern human's. The earliest definitive evidence of fire-making ability, the ability to actually create fire on demand rather than just maintaining natural fire from lightning strikes, doesn't appear until roughly 400,000 years ago at European Neanderthal sites, where researchers have found evidence of sparks being struck from flint and iron pyrite. Before that, there's some evidence of fire maintenance, of keeping a flame alive after finding one. Wonderwork Cave in South Africa, somewhere between 1 and 1.8 million years ago, contains burned bones deep inside the cave, far from where a natural wildfire could reach. That suggests someone carried fire in from outside and kept it going. Gesher Benot Yaakov in Israel, roughly 780,000 years ago, has evidence of cooked fish, which means controlled fire was being used. But maintained fire is fragile. It goes out. In rain, in wind, in snow, a carried flame can die, and if you can't make a new one, it's gone. Maybe for days, maybe forever. Dennis Sandgaith at Simon Fraser University has pointed out something else that makes this puzzle even harder. Fire evidence in the archaeological record sometimes disappears during the coldest glacial periods. The exact moments when fire would have been most useful, the harshest winters, the deepest ice ages, that's when the evidence thins out. Either people retreated south during the worst of it, abandoning the landscapes where fire evidence would be preserved, or fire truly wasn't a reliable universal tool yet, even for populations that sometimes had access to it. Here's a paradox that nobody has fully resolved. Fire evidence goes missing during the coldest periods, but people don't always go missing with it. Some stayed, some survived winters that should have been unsurvivable without fire. And the only explanation is the combination of everything we've already talked about: the biology, the shelter, the huddling, the diet, the strategic movement, all working together as a system that predates fire by hundreds of thousands of years. Now, there's one more piece of this story that deserves attention, because it changes how you think about animal skins. Most people assume that wearing animal hides requires fire. You kill the animal, skin it, tan the hide over a fire, smoke it for preservation, and then you have leather. But that's brain tanning, a sophisticated technology that does indeed require fire for the smoking stage. What about before that, raw hides work? Not well, not for long. A fresh animal skin draped over your body will keep wind off and trap some heat. If you let it dry while it's molded to your shape, it stiffens into something that holds its form. Rawhide is strong and, when dried, reasonably waterproof. The problem is that untanned skin rots in damp conditions and turns brittle in heat. It's a temporary solution. But temporary solutions keep you alive until you find a better one. And when the alternative is nothing between your skin and a sub-zero wind, a rotting deer hide is a significant improvement over philosophical objections about its shelf life. Evidence of skinning cave bears for their fur goes back roughly 300,000 years. At Contrabandier's Cave in Morocco, researchers found specialized bone tools for scraping and processing hides dating to between 120,000 and 90,000 years ago. The hides weren't just thrown over shoulders, they were being worked, shaped, prepared with specific tools designed for the purpose. This is the beginning of the clothing industry, and it starts not with needles and thread, but with a dead animal and a bone scraper. And then there's bedding at Border Cave in South Africa. Archaeologists found grass bedding laid over ash layers dating to roughly 200,000 years ago, the oldest known bedding in the world. At Sibudu Cave in KwaZulu-Natal, Professor Lynn Wadley of the University of the Witwatersrand published findings in Science in 2011 describing multi-layered sleeping mats made from sedges and rushes, dating to about 77,000 years ago. The mats were topped with leaves of Cryptocarya woodii, a plant with natural insecticidal and larvicidal properties. These people weren't just sleeping on whatever was lying around. They were selecting specific plants with specific chemical properties to keep bugs away from their beds without fire. A thick bed of grass between you and frozen ground is the difference between losing body heat through conduction all night and retaining enough of it to wake up in the morning. Grass is an insulator, not a great one. But physics doesn't care about great. Physics cares about whether the rate of heat loss from your body exceeds the rate of heat generation. Anything that slows the loss side of that equation, even slightly, extends your survival window. And extending your survival window by a few hours every night for an entire winter is what staying alive looks like when you don't have a fireplace. So let's put it all together, because the answer to how ancient humans survived winter without fire isn't one clever trick. It's an entire system, and every piece of that system had to work, or you died. Your body ran hotter than you'd expect, with brown fat generating heat internally and vasoconstriction redirecting blood to protect your core. You found shelter, a cave, if you were lucky, a windbreak of branches if you weren't. You slept in groups, bodies pressed together, pooling the thermal output of every person in the huddle. You ate the richest food you could find, raw meat and bone marrow packed with fat, and your gut generated heat as a byproduct of breaking it down. You covered yourself with animal skins that you scraped and shaped with bone tools. You slept on beds of grass that insulated you from the frozen ground, and when winter became truly unbearable, you moved. You drifted south, following the animals, following the warmth, retreating from the worst and returning when conditions allowed. No single one of those things would have been enough. Together they were, and then somewhere in that long, cold stretch of human history, someone figured out fire. Maybe they watched a lightning strike and grabbed what was left. Maybe they noticed sparks when they struck certain stones together. Maybe they maintained a natural flame for weeks, then months, then years, learning to feed it, learning to shelter it, learning that this fragile orange thing was the most important object in their entire world. And when fire became reliable, everything changed. Suddenly, you could cook food and extract twice the calories. You could stay warm in places that would have killed you before. You could harden tools. You could light the night. You could live where no fireless human had any business living, and not just survive, but build something. But for hundreds of thousands of years before that moment, your ancestors made it through winters that would flatten most modern humans in a week. They did it without the one thing we consider absolutely essential for cold weather survival. They did it with their bodies, their brains, each other, and an understanding of the natural world so deep and so detailed that it's difficult for us to even imagine from the warm side of a thermostat. The next time you flip on a heater and complain that your house is cold at 18 degrees, remember that somewhere in your DNA there is a record of people who slept on frozen ground, covered in raw animal skin, pressed against strangers, eating uncooked marrow from a cracked bone, waiting for a sun that wouldn't rise for another 14 hours. And they woke up, and they did it again the next night, and the next. You are here because they were very, very hard to kill.